Union, intersection and complement. An overview. Axioms of set theory imply the following. For any sets x and y, there exists a set Z with this property. Namely, U is a member of Z if and only if U is a member of X or U is a member of Y. So, for any sets x and y, we can form a set Z which contains members taken from X and Y, including those members which are in X alone, Y alone, or in both sets simultaneously. This formula is taken as a definition of the union operation on sets X and Y. So the union of X and Y is denoted using this symbol. This is the union symbol. And X union Y is the set Z which has this property. To visualize the union operation, consider sets X and Y as in this diagram. And then the union of the sets is the shaded area of the diagram. So anything which is in the set X or in the set Y, including the part which is common to X and Y. Some simple examples. Singleton of 1, union singleton of 3. We take the elements from these sets, we end up with the set containing 1 and 3. 1, the set containing 1 and 2. Union, the set containing 2 and 3. The result is the set containing 1, 2, 3. We just collect all the elements which appear in either set or in both. 2 occurs in both, and it is included in the result. Of course, we are including it once because there is no need for duplicating an element when we write a set. And another example, the set with 1 and 2, union the set with 1, 2, and 3. This is interesting in the way that the first set is a subset, a proper subset of the other. In such a case, the result is the bigger set. So the result is the set with 1, 2, and 3. Here is a fact which is really useful in improving properties of set operations. Z is a member of X union Y if and only if Z is a member of X or Z is a member of Y. This is something worth remembering. And we can negate each side of this equivalence, obtaining Z is not a member of X union Y if and only if, and now also the Morgan law is involved, which turns OR into an AND. So this is equivalent into Z is not in X and Z is not in Y. The next operation is that of intersection. Let X and Y be any sets. The intersection of X and Y is denoted with this symbol. This is the inverted symbol for the union. And X intersection Y is the set of those Z from X for which Z is a member of Y. It's good to think about it as the set of those Z that z is in x and z is in y. A visualization. Given sets x and y in this diagram, the intersection is the shaded area of the diagram. And an example, the pair 1, 2 intersected with the pair 2, 3 is the singleton of 2. This is the common part, and in this case the only common element in the two sets is the number 2. So think of intersection as the common part of x and y. Here is a fact which will be useful in proving properties of set operations. Z is a member of x intersection y if and only if Z is a member of x and Z is a member of y. Please notice the correspondence of the intersection operation and the AND operation from logic. And a negated version, the left-hand side of the equivalence is negated, resulting in Z is not a member of X intersection Y, if and only if, by the De Morgan law, AND turns into an OR, and we have Z is not in X or Z is not in Y. The next operation is that of a complement. Let X be a subset of a set U. We think of U as a universe of discourse. Whatever problem in mathematics we consider, there is some universe of objects which are under consideration. For instance, while considering problems in plane geometry, the universe of discourse is the set of points on a particular plane. While considering solutions of an algebraic equation, the universe of discourse is the set of real numbers, or maybe the set of complex numbers, depending on the problem. So U is going to be our chosen universe of discourse. This shouldn't be confused with the universal set. There is no universal set, as we proved earlier. But now let X be a subset of U, and we define the complement of X with respect to U. This is the set of those elements little u from capital U for which U is not in X. Such a set is denoted by X with the superscript C, provided that the universe of discourse is known from the context. We can visualize this concept as follows. Let U be the set of all the points in this rectangle, and X, let X be the points in a disk. Then X complement is the shaded area in the diagram. Example: the complement of the set of even integers. So we take the set of even integers and we take a complement with respect to the set of all integers. And the result then is the set of odd integers. The complement of the set of rational numbers with respect to the set of real numbers is the set of all irrational numbers. Here's an important, very basic but useful property of the complement. Z is a member of the complement of X if and only if Z is not a member of X for Z from the universe of discourse. And the negated version, Z is not a member of the complement of X if and only if Z is a member of X. And this is again for Z from the universe of discourse. The operations of union, intersection, and complement can be implemented on a computer. So first we need to think how we are going to represent sets in a computer. We will deal, in the case of computers, we'll deal with finite sets, and one common implementation is to take to represent a finite set of strings as a dynamic hash table. And it's with the understanding that a string belongs to the set if and only if it is a key in the hash table. And if so, inserting, deleting, testing membership become very efficient, average constant time operations. Union, intersection, and complement are average linear time operations. Another implementation which is much simpler to do, but is the following, and I will consider a simple case where the universe of discourse has just 8 elements, A0 through 7, A0 through A7. Any subset A of such a universe can be represented as a bit vector. To give an example, if you are thinking about the set A consisting of A0, A1, and A3, we represent it as a vector with 1s at positions 0, 1, and 3, with the remaining positions filled by zeros. In such a case, bitwise operations, bitwise OR, bitwise AND, bitwise complement correspond to the set operations of union, intersection, and complement. This is very efficient. The operations are performed in constant time. And one can consider universes bigger than the one I used. Actually the universe, using this idea, the universe could be of any size that fits in the memory allocated to the process. The operations are then constant time, but we need to be aware that this is actually proportional to the size of U. And some exercises. What's the complement of the empty set with respect to some set U? What's the complement of U with respect to U? What happens if you take a complement twice. True or false? Is the union operation commutative? Can you change the order of the components? The same question about the intersection. How would you complete the following? X union the empty set. X intersection the universe of this course. X intersection the empty set. X union the universe of this course. X union X. X intersection X. X union X complement. X intersection X complement. And here's a more challenging exercise. Complete this equivalence. X is a subset of Y if and only if X union Y equals what? To answer this question, I recommend that you make a diagram sketching sets X and Y such that X is a subset of Y, and then look at the part of the diagram which represents X union Y, and similarly for the remaining points of the exercise. Having a diagram is not a proof of an equality, but it's a good way of thinking about the problem. Once you have your answer based on a diagram, you should convince yourself that you should make sure that the answer holds in general.